So why are sine and cosine values useful? One of their applications is that they allow you to deduce missing information about a triangle. The 6 key pieces of information for any triangle are the lengths of the 3 sides and the values of the 3 angles. However, not all 6 of these measurements are always known. For example, you might know all 3 sides, but none of the angles. 2 sides and 1 angle, but not the other side and the other 2 angles, and etc. These 2 important rules, the sine rule and the cos rule, allow you to deduce all the missing information from a triangle from knowing only 3 out of 6 measurements. Therefore, from only 3 known sides, you can deduce the value of all the angles. From 2 sides and 1 angle, deduce the value of the last side and the other 2 angles. Or from 1 side and 2 angles, the value of all the other measurements. However, the only case where this does not work is when you know all 3 angles and none of the sides. Therefore, we always need to know at least one side of the triangle to deduce the rest of the information. Now let's look at the sine rule a bit more closely. It states that the ratio between the length of a side and the sine of the angle opposite to that side is the same for every side in a triangle. In other words, A over sine A is equal to B over sine B and is equal to C over sine C. I am going to prove this rule, and even though you do not need to know this proof for the IB math exams, I think it helps your understanding. First, let's prove the sine rule for an acute triangle. I am going to draw an altitude from the vertex between sides A and B to side C, and I'm going to call it H. From the definition of sine, we have sine A is equal to H over B, because H is the side opposite to A in this right angle triangle. We also have sine B is equal to H over A in this right triangle. You can rearrange these two to write H equals B sine A, and here H equals A sine B. And it's quite obvious that these two are equal. Therefore, from B sine A is equal to A sine B, we can write A over sine A is equal to B over sine B. Now to finish the proof and consider C and sine C, we just have to do the same thing for a different altitude. Now I will draw it from the vertex between sides A and C to side B. Using the same method, we would obtain the result. A sine C is equal to C sine A. And from here, A over sine A is equal to C over sine C. Therefore, B over sine B is also equal to C over sine C. And we have the sine rule for an acute triangle. With an obtuse triangle, things are a little bit different. With this altitude, in the same way, we obtain the result C sine B is equal to B sine C. To prove the same thing for the remaining side angle pair, we would have to draw an external altitude. Here we have an angle supplementary to A, and I will call it A dash. This part involves the rule. The sine of an angle is equal to the sine of the angle supplementary to it. Therefore, we have sine of A dash is equal to sine of A, and sine of A dash from this right angle triangle is in turn equal to H over B. And from this big right triangle, we also have sine b is equal to h over a. Again, we will have b sine a is equal to a sine b. When combining these two expressions, we obtain the sine rule for obtuse triangles. Now let's look at the cos rule in more detail. It states that side c squared is equal to side a squared plus side b squared minus 2 times a times b times cos of the angle opposite to c. Because the angle c is between a and b, you can also call it the included angle of a and b. Now, doesn't this rule look kind of like Pythagoras' theorem but for non-right angled triangles? As a bonus, can you figure out what happens when you apply the sine rule and cosine rules to right-angled triangles? Note that C is not the only side of the triangle that can work on the left-hand side of this rule. We could have e squared on the left-hand side, and the rule would simply look a bit different like this. Or a squared here. Basically, the cos rule applies to any pair of sides and the included angle on the right-hand side, and the other side of the triangle on the left-hand side, or either side of the equation. Again, I am going to prove the cos rule. You can skip the video if you don't have enough time. We have a triangle, and I'm going to draw an altitude on this triangle. Let's call it H. Now I will call this segment D, and this segment, this part here, E. From the definition of cos, we have cos C is equal to D over A. Therefore, D is equal to A cos C. Because E is equal to B minus D, it will be equal to B minus A cos C. Then from this right triangle, we have sine A is equal to H over C. So H is equal to C times sine A. Now applying Pythagoras' theorem on this triangle, we have C squared is equal to H squared plus E squared. Now we substitute these two expressions to H and E to get then we expand this. Now I'm going to do a little bit of rearranging. Have you noticed something about this part? Let's factor out a squared in this part. And from one of the identities that we covered previously, we know that sine squared c plus cos squared c is equal to 1. Therefore, this is all just equal to a squared. Basically, now we have the cos rule. Let's look at the first example where we know all three sides of the triangle but none of the angles. To find the measurements of the three angles, we will need to use the cosine rule first. You can apply it to any pair of sides, but I will choose angle BAC as the included angle between AB and AC. So with my cosine rule, I will have I'll plug in the numbers in. There's actually a version of the cos rule in the data booklet where the angle is the subject. You can use that version too. Either way, your answer should be that angle BAC is equal to 44.4 degrees to 1 decimal place. You can continue applying the cos rule for the remaining two angles, or try out the sine rule. I will use the sine rule here. BAC is opposite to BC, so we have again plugging the numbers in. Then using your calculator, you should find that ACB is equal to now the first time that you plug all this into your calculator, you'll probably obtain the answer that angle ABC is equal to 78.5 degrees. However, these three angles do not add up to 180 degrees as they should for the angles of a triangle. Besides, according to this diagram, angle ABC should be obtuse and not acute. Therefore, this answer cannot be correct. What we have to do instead is to use this rule and subtract 78.5 degrees from 180 to obtain the correct answer of 101.5 degrees. You can check that these three angles now add up to 180 degrees. And this is also an obtuse angle since it's greater than 90 degrees. In this next example, we are given two sides and one included angle. Let's first use the cos rule to find the remaining side. Your answer should be that AB is equal to 2 times the square root of 7, or 5.29 to 3 significant figures. Now I am going to use the sine rule to find the remaining two angles. Now we have all the measurements of this triangle. This time we are given one side and two angles. A helpful thing to remember is that if you know two angles of a triangle, then you already know the last angle, thanks to the fact that all of the angles add up to 180 degrees. Without using any sine or cosine rule, we can already calculate that ACB is equal to 70 degrees. In our fourth example, we have this triangle where we are given the measure of two sides and one non-included angle. You can use the sine rule to find the measure of angle CAB, then use the sum of angles property to find angle ACB. Or you can use the cos rule right from the beginning to find side AB first. That's what I'm going to do here.
numbers again.
Just use the equation solver function in your calculator and you'll find that AC has the length of 4.24 units to 3 significant figures. Now I am going to use the sine rule to find angle CAB. Now if you remember the rule about sine of supplementary angles, then you will find out that there are two possible answers for CAB based on this. CAB could be 25.4 degrees or 180 degrees minus 25.4. Which is 154.6 degrees. This time, let's not just rely on the diagram alone to decide which one suits CAB better. Instead, let's check using the sum of angles properties. If CAB is equal to 25.4 degrees, angle BCA would just be equal to 180 minus 40 minus 25.4. And that will be 114.6. And no problem here. However, if CAB is equal to 154, this gives us a negative answer of minus 14 degrees, which is not possible for a real triangle. Now, if you have chosen to use the sine rule here to find angle BCA, then you have chosen the trickier path. You will get something like this. And from there, the two possible answers: 65.3 degrees or around 115 degrees. If you don't want to rely on the diagram and choose which one fits best out of these two answers, which you shouldn't because the pictures are not always given accurately to scale, you would have to find angle CAB. Then substitute your answer for each case into this equation to see if they match. One of your answers for CAB will not be correct, and the measurement for BCA that led to this incorrect answer, which in this case is 65.3 degrees, will need to be eliminated. This will be the last example for this video. Again, you can use the cos rule to find side AB first, or use the sine rule to find angle CBA first. Let's use the sine rule to find the remaining angles now. Again, there will be two possible answers for CBA. Now let's use the sum of angles property to find the last angle BCA. There seems to be no problem here in either case. If you extend the sine rule to check which of these two answers are correct, you will find that this equation holds for the case where CBA is equal to 74.6 and BCA is 65.4. Unfortunately, now I have to point out a mistake that I made. This quadratic equation has two real roots that are both greater than 0. So there are actually two possible values for AB. 2.83 or 1.77. I only wrote one down because I chose the equation solver mode on my calculator where only one solution is displayed. Now if we apply the sine rule for the case where AB is 1.77 instead, we would find that the other case where CBA is 105.4 and BCA is 34.6 to be correct. But if this situation where there are two possible answers pop up in exams, then there will likely be more information that will help you decide which one is the correct answer. If we want to draw the triangle for the case where AB is 1.77, it will look like this. So be careful for cases where you are given two sides and one non-included angle. There is a chance of more than one possible answer. Now you know how to use the sine rule and cos rules. Just be careful in cases where there could be more than one answer. Thanks for watching.